dear students. Today we will study about real numbers for class 10th. And our today's topic is revisiting rational numbers and their decimal expansions. All of you have studied rational numbers from your lower classes, and you know that rational numbers are those numbers which can be written in the form of P upon Q, and Q is not equal to 0. So we'll study about these. The learning outcomes of this topic. At the end of this topic, you will be able to divide the rational numbers which are in the form of P upon Q into two categories, terminating and non-terminating repeating. You will also be able to convert the rational numbers into decimals when they are having terminating decimal expansion without actually dividing them. So today we will start from the rational numbers. All of you know that rational numbers are the numbers which can be written in the form of P upon Q, and Q is not equal to 0. Again, whenever you divide these numbers by its denominator, you will get a decimal expansion which is of the form either terminating or non-terminating repeating. Now we'll take some examples. 5 by 2. First example, 2.5 in decimal form and it is terminating. Terminating means it's after decimal, some digits after no repetition is there, and its answer is in the form of terminating number and remainder becomes 0. In case second, 17 upon 5, whose decimal expansion 3 upon 4, which is terminating, and third one is 8 upon 15. Its decimal expansion is 0.533 and so on. This is non-terminating and repeating. Fourth one is 9 upon 20. Its decimal form is 0.45. This is also terminating. Then next is 17 upon 6, whose decimal expansion is 2.833 and so on. This is also non-terminating repeating. 11 upon 21, whose decimal expansion is 0.523809, 523,809 and so on. So this is also non-terminating repeating. As you know that the number first, number second and number fourth, these are having terminating decimal expansions. Now we can carefully observe the denominator of these numbers. In first case, the denominator is 2. Second case, denominator is 5. And in third case, denominator is 20, whose prime factors are 2 raised to power 2 into 5. So in all these three cases, we can see that the denominator is, if it is factorized, then we get 2 or 5 or both 2 and 5. But in case of the other one, that is non-terminating repeating, our examples are 8 upon 15, whose denominator is 15, prime factors are 3 into 5. Next one, 17 upon 6, denominator is having prime factors 2 and 3. And 11 upon 21, it's also denominator have factors 3 into 7. So in all these cases, we can conclude that whenever a prime factor of the denominator Q is of the form 2 raised to power n into 5 raised to power m, then the rational number is having terminating decimal expansion. Similarly, when the prime factorization of the denominator Q is not of the form 2 raised to power n into 5 raised to power m, then the rational number is having non-terminating repeating decimal expansion. We can easily write them as, in the case of terminating decimal expansion, Q is equal to 2 raised to power n into 5 raised to the power m, where n, m are integers. And if non-terminating repeating decimal expansion, Q is of the form 2 raised to power n into 5 raised to power m into k, where k is a prime number other than 2 and 5. So with this method or with this property, you can easily find out at just a look that whether the rational number is having terminating decimal expansion or non-terminating decimal expansion. Now we have the theorem 1.5. Let x be a rational number whose decimal expansion terminates. And then x can be expressed in the form of p upon q, where p and q are co-prime and the prime factorization of q is of the form 2 raised to power n into 5 raised to power m, where n, m are non-negative integers. For example, we'll take first example 0.375. This is our first example. This is the rational number whose decimal expansion terminating. So I will change it into fractions, p upon q. This is equal to 375 upon 1000, which is equal to 375 upon 10 raised to power 3. Now I will factorize the numerator also. I will get 3 into 5 raised to power 3 upon 2 raised to power 3 into 5 raised to power 3. Now you can see 5 raised to power 3 will cancel out, and finally I will get 3 upon 2 raised to power 3. So the denominator is only having 2 in its prime factors. Second example is 0.104. Again I will change into p upon q form. 104 upon 1000, which is equal to 104 upon 10 raised to power 3. And this will also give me as 13 into 2 raised to power 3 upon 2 raised to power 3 into 5 raised to power 3. Again 2 raised to power 3 is cancelled out, and I am having left with 13 upon 5 raised to power 3. And my third example is 23.3408. When I will change it into the form of p upon q, it will be 2,33,408 divided by 10,000. I can also write it as 2,33,408 divided by 10 raised to power 4. And when I will factorize this number, I will get 2 raised to the power 6 into 7 into 521 divided by 2 raised to power 4 into 5 raised to power 4. And after cancelling, in the shortest form I will get 2 raised to the power 2 into 7 into 521 divided by 5 raised to power 4. So in all these three cases, you can see that whenever I have the rational numbers of the form terminating decimal expansion, I will get in the form of p upon q. The prime factors of q are either of 2 or having 5 or having both. So we can find out this result. Now the next theorem is, let x is equal to p upon q be a rational number such that the prime factorization of q is of the form 2 raised to the power n into 5 raised to the power m, where n, m are non-negative integers, then x has a decimal expansion which terminates. The rational number is given in the form of p upon q. Example is 3 by 8. Now prime factors of denominator, they are 2 raised to power 3. It is in the form of 2 or 5. Now for changing it into the decimals, I will make it multiply with 5 raised to power 3 in the numerator as well as in the denominator. Why I will multiply with 5 raised to power 3? Because when we multiply 2 raised to the power 3 with 5 raised to the power 3, it will become 10 raised to power 3. And in any rational number, when denominator is in the form 10 raised to the power any number, then it will be very easy to change it into the decimal form. Now I will get 3 into 125 divided by 10 raised to power 3, which is equal to 375 divided by 10 raised to power 3, or I can write it as 2 divided by 1000, 0.375. Hence, we can say this is terminating decimal expansion. Now, the next example is 13 upon 125. Again, I will factorize the denominator. I will get 13 upon 5 raised to power 3. So, it will change into 13 into 2 raised to power 3 upon 2 raised to power 3 into 5 raised to power 3. Why I multiply with 2 raised to power 3? To make it 10 raised to power 3. So I will get 13 multiply 8, 10 raised to power 3, 104 upon 10 raised to power 3, which is equal to 0.104. And my third example is 7 upon 80. Again, the factors of 80, we have only 5 in the denominator. Now I need, if there is 2 raised to power 4, I need 5 raised to power 4. So I need 5 3 times more. So I will multiply in the numerator and denominator with 5 raised to power 3. I can also write it as 7 into 5 raised to power 3 upon 2 raised to power 4, 5 raised to power 4. Finally, I will get 125 and 10 raised to power 4. This is 875 divided by 10 raised to power 4. And in decimal form, it will be 0.0875. So from these 3 examples, we can conclude that if the denominator of any rational number is of the form 2 raised to the power n only, or 5 raised to the power m only, or it have the form 2 raised to the power n or into 5 raised to the power m, then the decimal expansion of that rational number will be terminating decimal expansion. Now we'll come to the next theorem. Theorem 1.7, let x is equal to p upon q with a rational number such that the prime factorization of q is not of the form 2 raised to power n into 5 raised to power m, where n, m are non-negative integers, then x has a decimal expansion which is non-terminating repeating. This theorem is just opposite the theorem 1.6. We will understand this theorem with the help of some examples. My first example is 1 upon 7. The denominator of this rational number is not of the form 2 raised to the power n into 5 raised to the power m. It is 7, and which is other than 2 and 5. Now we will change it into the decimal form, which is equal to 0.142857. 142857. This complete unit is repeating, so I put bar on it. Right? Now I can take another example, which is 1 upon 3. And this decimal expansion is 0.333 and so on, which is equal to 0.3 bar. Now in both the cases, the denominator q is not having the prime factors of the form 2 raised to the power n into 5 raised to the power m. It is other than 2 and 5, and hence in both the cases the decimal expansion is not terminating and it is also repeating. Hence we can conclude that the rational number which is not having the prime factors of its denominator of the form 2 raised to the power n into 5 raised to power m is having decimal expansion non-terminating and repeating. Let's see example. Without actually performing long division, state whether the following rational numbers will have a terminating decimal or a non-terminating repeating decimal expansion. So first is 13 upon 3125. So my first step is to factorize the denominator, and I have 5 into 5 into 5 into 5 into 5, which is equal to 13 upon 5 raised to the power 5. Now you can see what is the denominator. It is 5 raised to power 5. So the prime factors of the denominator is only having 5 in its prime factors, so it is terminating decimal expansion, right? Second example. I will take second example 17 upon 8. So prime factors of the denominator 2 raised to power 3. Here also denominator is having only 2, hence terminating. Third one, 64 upon 455. Now prime factors of 455 are 5 into 7 into 13. In this case, students, we are having the prime factors in the denominator 7 and 13. These two factors are other than 2 and 5. So, in this case, we are having non-terminating and repeating decimal expansion. Which type of decimal expansion? Non-terminating, repeating. Next, fourth one is 23 upon 2 raised to the power 3 into 5 raised to the power 2. Students, in this case, the denominator is having the prime factors 2 and 5 both. Hence, which type of decimal expansion it will be? It will be terminating decimal expansion. Right? All of you got it? So in this way, students, you can do the other questions of the exercise. Now, homework for you. Question is, the following real numbers have the decimal expansion as given below. In each of the case, you have to decide whether they are rational or not. If they are rational and of the form P upon Q, what can you say about the prime factors of Q? And the questions are here. 43.12345678 0.1201201200120000 and so on. And the last one 43.12345678 We can also write it as a bar on this and leaving all these last digits because it is repeating. The next question is, without actually performing the long division, state whether the following of the rational numbers will have a terminating decimal expansion or not. If yes, then convert into decimals. So your first part is 15 upon 1600. Second part 29 upon 343. Third one is 77 upon 210. Fourth one is 35 upon 50. And fifth one 6 upon 15. So students, that's all about this topic, revisiting the rational numbers, their decimal expansions. Good day students. Thank you.